When we started the section about finding the magnetic force on a moving charge, we began by saying we knew there was a force on a moving charge by thinking about a simple DC motor. And a DC motor was created from a current carrying wire. It experienced a force, so those charges must have had forces. Now we're going to back up to things like that DC motor and ask, how do we find the force on the current carrying wire? So it's still a similar thing, but instead of looking at an individual charge, we're going to look at the current. To find the magnetic force on a current carrying wire, let's start with the expression for the magnetic force on a moving charge. FB equals QV cross B. Let's remember that velocity is distance over time. So let's put that in. So FB equals Q times delta X over delta T crossed with the magnetic field B. And my F is a vector as well. Okay, now let's just look at Q and delta T. Q and delta T would be current. So current is charge over time. And then we can treat our delta X as a length of wire. So we can say that delta X is along a length of wire. And we could keep it as delta X, but we more typically write it as L. So that leaves us with our magnetic force on a current carrying wire is equal to IL cross B. The only thing maybe to really notice about this equation is that L is marked as a vector. The direction of the L vector is the same as the direction of current flow. So you can do this either by using your right-hand rule or either by using your equation for cross products, or you can do magnitude and direction. The magnitude of the magnetic force would be the magnitude of current times the magnitude of the length times the magnitude of B times sine of the angle between L and B. So you can do that for your magnitude, or you can do your right-hand rule where your thumb points in the direction of your first vector, that's L, or in the direction of current, I. Your index finger is your second vector, that's B, and your extended middle finger is your resultant, that's your magnetic force. Okay, we'll do 3 really quick examples. What if we had a wire and the current was 0? What would happen to that wire? Well, FB equals IL cross B equals 0. So what would happen to this wire is nothing. Okay, no current means no force, no motion. So next, let's say we have our wire and we have current flow in our wire where the current goes straight up. What would happen to that wire?
If the current flows up, we'll use our right-hand rule. Force is IL cross B. Our thumb is our current, so the current goes up. We cross it with the magnetic field, that's into the page, and we look at what direction our finger points to give our force. So there's the direction of the magnetic force when the current comes up. Pulls this way, so the wire will distend this way.
Okay, so our magnetic force is in this direction, which means that overall that wire is going to bow outwards to the left. And then for the last example, what if we had our current carrying wire and we flip the current and the current now flows downwards?
To find the direction of the magnetic force when the current moves down, we'll still use our right-hand rule. Current is down, so your thumb is down. Magnetic field is into the page, so your index finger is into the page. Your extended middle finger shows the magnetic force, so the force points this way, so the wire will extend out this way.
Okay, the magnetic force is to the right, which means that the wire bows out to the right. So in this example, we have a simple circuit. We've got a 3 ohm resistor attached to a 15-volt battery, and the right end of the circuit extends into a place where there's a magnetic field of 50 milliteslas pointing into the page. What are the magnitude and the direction of the net force on the circuit? Well, our equation for magnetic force on a current carrying wire, F equals IL cross B. That's what we'll use to figure this out. We notice that there's a current in it, so why don't we see if we can find the current before we get started. So the current comes out of our battery this way, extends along here, down and around here, back in around here. So there's our current I. It's a simple circuit, so if we remember Ohm's law, V equals IR, then I is equal to V divided by R. 15 volts over 3 ohms equals 5 amps. Okay, there's the current in our circuit. I suppose I should keep a few sig figs there. 5 amps. There's the current in our circuit. Now let's think about our forces. Remember, there's a force on every wire that's carrying current and is sitting in a magnetic field. That applies to 3 sections of our circuit. So along the top here, we have this wire. That color's not very good. This part of the wire is in a magnetic field. It's carrying current I and it's in the field. The length of the bit that's in the field, let's call that little I, little l. We can do our right hand rule to find the direction. You point your thumb to the right because that's the direction of the current. Your index finger goes into the page. Your extended middle finger should point up and we'll see a force that points up. So there's the force for the top segment. Okay, while we're thinking about the top, let's go down and do the bottom. Same length of wire is in the field on the bottom, but now the current goes the opposite direction, so the force on that bottom segment points down. You might already have an idea what's going to happen to those two guys. And then the last segment will be the segment that's vertical in the field. So the current points down, you put your thumb with the current, your index with the field into the page. You should see that your extended middle finger points to the right. So that's the direction of the magnetic field on the side. That length we see is 10 centimeters, and we'll probably call that L. Okay, to get our net force, we're going to have to add them all up. Sum of the forces equals F of the top plus F of the bottom plus F of the side. And those are all vectors, of course. Okay, so my force for the top is equal to, the magnitude is the magnitude of the current times the length times B, and the direction is straight up. We found that with our right-hand rule. For the bottom, the magnitude is ILB, because it's the same current times the same length times the same field, but this time the direction is straight down, negative J hat. So these two guys together, they add to give 0. So my net force is just the force on the side part. Okay, the force on the side part, we'll do IL cross B. My current, we already found that, that was 5 amps. My L is the length of the wire, that's 0.10 meters, that's shown in the diagram. L is in the same direction as the current. The current flows down, so the direction is minus J hat. And that's crossed with the magnetic field, which is into the page. Let's get our coordinate system on there. Into the page is minus K hat, and the magnetic field is minus 50, is 50 milliteslas. So I've got minus 0.050 teslas K hat. In doing this calculation, I can multiply my numbers. 5 times minus 0.1 times minus 0.05. That'll give me plus 0.025. That's in newtons. Then I'm left with J hat cross K. J hat cross K gives us I. 0.025 newtons I hat. We'd already found the direction of the force from our right-hand rule, but it's absolutely legitimate to find it from using the cross product as well. So now let's ask the question, what if our wire is not straight? What if we have something with a curve? And that's what this example is showing here. We take a solid wire, we bend it into the shape of a semicircle with radius r. It's a closed circuit and it's carrying current I. I'm going to say that my I goes to the right along the bottom segment and counterclockwise in the top segment. So there's my current. We're asked to find the magnetic force on the straight portion and on the curved portion. Okay, the straight portion is not going to be so hard. Let's do that first. I'll put in my coordinate system, x, y, and z. So for the straight portion, my magnetic force, FB, equals IL cross B. The only part that's a little bit tricky here would be my L. The radius of the circle is R. So the length of this bottom segment, L, would be twice the radius. So I've got I times L. The direction of L is the same as the direction of I, so that's to the right, in the I hat direction. So I've got 2R I hat. That's crossed with my magnetic field, and the problem says a uniform magnetic field is present along the positive y-axis. So these up arrows are showing the magnetic field. So that's B, J hat. I'll haul my constants all out to the front. 2 times I times R times B, I cross J. I cross J is equal to K. So my magnetic force on the straight portion equals 2IRB K hat, or straight out of the page. So that magnetic force on the bottom part points out. What about the magnetic force on the top part? I think I'll just go on to a fresh slide before I start that one. Finding the magnetic force on the curved portion is going to be a little bit more difficult. When we write the equation for magnetic force equals IL cross B, this equation is easy to do if your L is constant, but our L is not constant. And the reason it's not constant is that because for the curved portion, the direction of L is always changing. So now what we've got to do is back up and think, is there another way to do it? Well, what if we picked a little segment of that wire and we said that had length ds, and I'm choosing ds because it's a little bit along a circle, then that little bit of segment would make a little bit of force, df. That little bit of force would be equal to I times ds crossed with b. Then if I wanted to find the net magnetic force, I would have to add up all the little bits. So my net magnetic force would be the sum, or the integral, of each of those small bits. So the integral of I times ds cross b. So this seems like a solid strategy. Let's go ahead and let's find the magnitude first, and then we'll find the direction afterwards. So let's start with magnitude. The magnitude of FB is going to be the integral of the magnitude of dFB, which is equal to the integral of I times the magnitude of ds cross b. The magnitude of ds cross b is equal to the magnitude of ds times the magnitude of b times the sine of the angle between them. Okay, let's start to put this together in doing an integral. You might remember from your high school geometry class that arc length s is equal to radius times theta, which tells us that a little bit of arc length ds is equal to the radius times a little bit of arc length d theta. So now that we've written down r and theta, let's get those in our picture. R is the radius of the circle, so it goes from the center up to our ds. And then theta is the angle that it makes, the angle that it subtends. Okay, let's keep going with our process. So now the magnitude of FB is equal to the integral of current times R times B times sine theta times d theta. I just put my d theta at the very end because that's a typical way to do it in a math class. We can take our constants out front, I, R, B, integral of sine theta d theta. Can't get away from the limits any longer, so what are our limits of theta? Well, our limits will go from one end of the curved rod to the other. Our first end of the curved rod is down here. This is where theta equals 0. And our final end of the curved rod is over here. This is where theta is equal to pi. So the limits are from theta to pi. Okay, next step in the integral. We've got I times R times B. The integral of sine is minus cosine. That's going to be evaluated at pi and 0, so we'll put in our limits. Got minus cosine of pi minus cosine of 0. I think I have just enough room to get my answer in here. Cosine, actually maybe I don't. Cosine of pi is minus 1. Cosine of 0 is 1, so I've got 1 plus 1. That part's going to be equal to 2. I'm totally out of space, so I'm going to go on to the next slide. So that gives us for the magnitude of our magnetic force equal to I times R times B times 2. We need a direction for our magnetic force. We'll apply our right-hand rule. You put your thumb in the direction of ds. That's kind of up and to the left. Put your index finger in the direction of B. That's straight up. You extend your middle finger and you should see it pointing to the page. That's true no matter where you pick ds on this arc. If you don't believe me, you can try it out. Pick some pieces of ds over on the right, pick one up on the top, pick one over on the left. You'll always get your magnetic force into the page. So let's write down our magnetic force on the top part as a vector. Minus 2IRB times 2 into the page k hat. It's a little dissatisfying to have the 2 at the end. I think I'll put it at the beginning. Okay, so this is all the problem asked us for, but let's just take it a little bit further and let's think about the net force on our little loop. So the force on the top curved part of the wire is minus 2RB k hat, so 2IRB into the page. The force on the bottom part is 2IRB out of the page. So the net force on our loop is 2IRB k hat minus 2IRB k hat equals 0. So there's no net force on that loop. So a good question to ask is, does it move? I would have to say that it can't sort of move up or down, left or right. It doesn't translate. And that's kind of what F equals ma is talking about. It's talking about the acceleration of the center of mass. The center of this mass doesn't move at all. But the top part gets pushed into the page, the bottom part gets pushed out of the page. This thing can actually rotate around some axis, so there will be rotation. So if we ask, does it move? The overall answer has to be yes, and it will rotate. And if you ask why it rotates, that means there must be a torque. We're not going to stop and talk about torques right now, but we are going to come back around to torques. It is good to start building the basis though as we go.